Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem having been chosen from the same book, Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay, a particular radiating cavity has the maximum of its spectral distribution of radiated power at a wavelength of 27.0 millimeter in the infrared region of the spectrum. The temperature is then changed so that the total power radiated by the cavity doubles. Part A. Compute the new temperature. Part B. At what wavelength does the new spectral distribution have its maximum range? Question not very tricky, almost simple. We have to find out two things. Okay, the first is the temperature and second is the wavelength. Okay, so now we move to its solution, but before starting our solution in a formal manner, we will have to go through a few snapshots. These snapshots will provide us a foundation regarding the solution of this problem. Snapshot here means a portion from any book of physics which is quite relevant to our situation of the problem. Okay, so in this problem we will go through two snapshots. Okay, in the first snapshot, Wein displacement law for a black body has been described or defined. Okay, and in the second, Stefan Boltzmann law for a black body has been defined or described mathematically. Okay, so first snapshot regarding Wein displacement law for a black body. Okay, Wein displacement law for a black body, lambda mt is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. Here lambda m is the peak wavelength in spectral emittance curve. Okay, m means maximum or peak. Okay, lambda we know that always denote wavelength. Okay, so lambda m, that is maximum wavelength or peak wavelength in spectral emittance curve, and capital T is the absolute temperature of black body. Okay, is equal to 2.90 into 10 to power minus 3 meter Kelvin. Okay, second snapshot is about Stefan Boltzmann law for a black body. According to this law, I is equal to sigma T raised to the power 4. Okay, here I is the intensity of radiation from black body. Okay, I is the intensity of radiation from black body, and sigma is Stefan Boltzmann constant, while capital T is the absolute temperature of black body. Dear students, this sigma, that is Stefan Boltzmann constant, I think is called sigma or summation. Anyhow, even if this Greek letter is pronounced differently, it is not a major irregularity. Okay, I think this is sigma or summation. Okay, so in the light of these two snapshots, now we are going to start our solution in a regular manner. Okay, formal manner. Part A. According to Wein displacement law for a black body, lambda m, that is peak wavelength or maximum wavelength into absolute temperature T, is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. This implies that if we keep absolute temperature T on one side, then peak wavelength or maximum wavelength lambda m will be divided on other side of the equality. That is to say, in the first stage it is in the numerator, while after being shifted on other side of the equality it will appear in denominator. Okay, so this implies that T is equal to 2.90 to 10 raised to the power minus m. Students, according to Wein displacement law, lambda m T is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. When T is kept on one side, then lambda m will be divided on other side of the equality and it will appear in denominator. Okay, so T will become equal to this. In the next step, we are going to put the value of lambda m, which is provided in the statement, which is 27.0 into 10 raised to the power minus 6 meter. Okay, dear students, here meter will be cancelled with meter and our answer will be only in K, that is absolute temperature. So next, just simplification, nothing else, just simplification. And after simplification, our absolute temperature T will become equal to 107 Kelvin. Okay, prior to this, in the second last stage, it becomes 0.107 into 10 raised to the power 3 Kelvin. But when we multiply 0.107 with 1000, then it becomes complete 107. Okay, so our absolute temperature T has become equal to 107 Kelvin. Now, dear students, we are developing some foundation regarding the solution of the next portion of this problem. Okay, so our foundation will be based on this philosophy. Okay, a body that absorbs all radiation incident on it is called an ideal black body. In 1879, Joseph Stefan formed an empirical relation between the power radiated by an ideal black body and the temperature, R equal to sigma T raised to the power 4, equation number 1, where capital R is the power radiated per unit area and capital T is the absolute temperature, and sigma is equal to 5.6703 into 10 raised to the power minus 8 watt per meter square Kelvin raised to the power 4 is a constant called Stefan constant. Okay, this constant is given in various tables of physical constants. Okay, this constant is called Stefan's constant. Okay. This result was also derived on the basis of classical thermodynamics by Ludwig Boltzmann about 5 years later, and equation 1 above is now called the Stefan-Boltzmann law. Okay, dear students, in our snapshot we have explained this Stefan-Boltzmann law in detail. Okay, let T1 and T2 be the old and new temperatures respectively. Then this implies that T1 is equal to 107 Kelvin, which we have calculated in the previous part of this problem, and this temperature will be treated as first temperature. That is, first temperature is denoted by T1 and new temperature is denoted by T2, which we are now going to find out. Okay, let T1 and T2 be the old and new temperatures respectively. This implies that T1 is equal to 107 Kelvin and T2 is yet to be determined. Similarly, let R1 and R2 be the old and new powers radiated by the cavity respectively. Then this implies that R2 is equal to 2R1, because this condition is provided in the statement that power becomes double. Power radiated becomes double. So it means new power radiated, that is R2, is twice the previous original power radiated. That is, R2 is equal to 2R1. Now, as per given condition, R1 is equal to sigma T1 raised to the power 4 and R2 is equal to sigma T2 raised to the power 4. What is this? This is Stefan-Boltzmann law. Okay, this has been applied separately for both pair of values. Okay, R1 is equal to sigma T1 raised to the power 4 and R2 is equal to sigma T2 raised to the power 4, while it is provided in the statement that subsequent power radiated is twice the original power radiated, that is R2 is equal to 2R1. Then this implies that according to this situation provided in this statement, sigma T2 raised to the power 4 becomes equal to 2 sigma T1 raised to the power 4. Okay, from here sigma will be cancelled with sigma and we will get, this implies that T2 raised to the power 4 becomes equal to 2 T1 raised to the power 4. This implies that if we take 1 by 4th power on both sides, then this implies that T2 raised to the power 4 raised to the power 1 by 4 is equal to 2T1 raised to the power 4 whole raised to the power 1 by 4. This implies that T2 becomes equal to, because 4 will be cancelled with 1 by 4 and we will be left with only T2. Okay, so this implies that T2 becomes equal to 2 raised to the power 1 by 4 into T1, because T1 will also be left alone because its 4th power will be cancelled out with 1 by 4th power. Okay, so T2 becomes equal to 2 raised to the power 1 by 4 into T1. We have value of T1 which we have calculated in the starting portion of this problem, which had become 107 Kelvin, and moreover we can find the value of 2 raised to the power 1 by 4. we can write 2 raised to the power 1 by 4 as 2 under root power 1 by 2, because under root is also 1 by 2. Okay, so 2 raised to the power 1 by 4 can be written as 2 raised to the power 1 by 2 into 1 by 2. Okay, it while we know that value of 2 under root is 1.41, and this 1 by 2 has taken the shape of once again under root. Okay, so this, that is 1.41 is the value of 2 under root, while this under root sign is equivalent to this 1 by 2 power. Okay, so this is quite a simple simplification. We should not explain it in more detail. Okay, quite simple. In other words, we can say that we can directly find the value of 2 raised to the power 1 by 4, which will become equal to 1.19. We have split this answer in 2 steps, that is 2 under root raised to the power 1 by 2. Why 2 under root is also 2 raised to the power 1 by 2 and then again 1 by 2. Okay, so I leave this discussion here. Okay, value of 2 raised to the power 1 by 4 is equal to 1.19, and it will be multiplied with 107 Kelvin, and our answer will become equal to 127.25 Kelvin. What is this? This is T2. Okay, so our T2 has become finally equal to 127.25 Kelvin. Now we are moving towards part B, which is dealt with according to Wein displacement law. Okay, so part B of this problem, according to Wein displacement law for a black body, lambda mt, that is peak or maximum wavelength into absolute temperature, is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. Here, if we keep peak or maximum wavelength on one side, then absolute temperature T, which is primarily in the numerator, will be shifted to denominator after being shifted on other side of the equality, and hence we will get lambda m, or peak or maximum wavelength, is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin over T. Okay, so in the next step we are just using the value of T, which we have found in the previous step or previous part of this problem, which was 127.25. okay, Kelvin. Here Kelvin will be cancelled with Kelvin, and we will be left with 2.90 meter divided by 127.250. How this value has been changed? This value actually, dear students, this value 10 raised to the power minus 3 will be shifted to denominator, and it will become 10 raised to the power plus 3, that is 1000. When we will multiply 1000 with 127.250, then it will become 127.250. Okay, quite simple. It is just a simplification. In the next step, we have shifted the decimal one step ahead, due to which we have to increase one more zero in the denominator. Okay, in the next step, it has become 29 meter divided by 127.2500. Okay, we can directly write its answer as this, but it is just manual setting regarding simplification of this numerator and denominator. Okay, so it has become equal to 2.28 into 10 raised to the power minus 5 meter. To this extent, our answer is 100% complete. However, as a matter of discretion, we can reshape this result as 22.8 into 10 raised to the power minus 6 meter. Why we have done so? Actually, dear students, because 10 raised to the power minus 6 is called micro. Okay, we know that 10 raised to the power minus 6 is called micro, while 10 raised to the power plus 6 is called million or mega. Similarly, 10 raised to the power minus 9 is called nano, while 10 raised to the power plus 9 is called giga, and so on. So this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.